Hello. Good evening, everyone. Today is the second problem solving session of fluid flow operations. So, we will be studying the questions or solutions related to the fluid static, what we have learned in this week 2. So, I'll be starting in 2 minutes. So, I hope my screen is visible. So, today is the week 2 of fluid flow operations. So, I'll first go through the lecture notes that sir has done. So, uh, so what is fluid statics? So, fluid statics is concerned with the balance of forces which stabilizes the fluids at rest. That means, suppose that means this there is a solution. Okay, suppose there is a water, and inside it a box is there. Okay, it is floating, but the fluid is static. Fluid is not moving anywhere, right? So here we will have some pressure, right? So basic pressures are mg, that is the gravitational force, upper side, that is the buoyancy force, like that. Okay, there are some other pressures also. Okay, so there are frictional force kind of thing. So this study is called the fluid statics. Okay, so here you will see that the pressure is different at different positions. So if you notice, so pressure in this point is suppose P1, and pressure in this point suppose P2. So this pressure, both the pressures are not same. So P1 is not equals to P2. So there is a pressure difference associated with the height of the object or inside the liquid. Okay, so that is what it is talking about. So you can see this like pressure in fluids at rest. That means the fluid is not moving. Fluid is at rest. Okay. So what is there in this case? So how pressure is defined? Now we'll know the definition of pressure. So here we are talking about normal pressure. Normal pressure. Okay. So last class we have seen the shear stress, right? So both are pressure. Both are pressure and both have a unit of Pascal. Then what is the difference? So if there is an object, if there is an object, okay, so the pressure acting normal is called the normal pressure. This is the normal pressure, okay, and the pressure acting at the tangential direction, this is the shear pressure. This is the shear pressure, or we call it shear stress, which is defined by tau, right? And this is the normal pressure is P. Okay, both of them is called the force per unit area, and similarly their unit is Newton per meter square or Pascal, right? So this is what it is said. Okay, so we know that the atmospheric pressure is the pressure at the atmosphere, which is equivalent to 760 millimeter hertz, right? Millimeter Hg, and this is equivalent to the 101325 Pascal or 101.3 kilopascal, right? Next comes the concept of absolute pressure. So absolute pressure is, what it is told that based on the perfect vacuum it is called absolute pressure, and based on the atmospheric pressure it is called the gauge pressure, right? So definition is gauge pressure is absolute pressure minus atmospheric pressure, right? So what it is absolute pressure? So absolute so absolute pressure is atmospheric pressure plus gauge pressure, okay? And if this is happening in the vacuum, then absolute pressure equals to atmospheric pressure minus vacuum pressure, okay? So it is the difference. So this is the same thing they are explaining. So this is the it is shown here that how the height is affecting the pressure of water or pressure of any liquid. You can see, right? So the top water jet has the low pressure and the bottom most water jet has the highest pressure, right? So in a building, you can think the person living in the top floor is getting a low pressure water jet. However, the person staying in the ground floor may get the highest pressure water jet, right? So this is the difference of pressure with height. So this is the mathematical calculation of characteristic pressure. So how this normal pressure is acting, and these are the some calculations. So you must have gone through that. So I'm not repeating. I'll be directly jumping into the equations or solving questions. So let's start that. So the first question is, the stresses associated with a static fluid is or are. The stresses associated with a static fluid. The stresses associated with a static fluid. So as I have said earlier that the fluid is not moving. The fluid is not moving. So what will happen? It will not have any shear stress because nothing is flowing. Nothing is there at the interface of this liquid and solid. That means it is not moving. So between them there is no force. So here shear stress will not be there. So the answer is normal stress. The answer is normal stress. So this is the only, because if there is any shear, that means the fluid is flowing, right? But we have said that it is a static fluid. That means the fluid is stagnant. Next. Absolute pressure is defined as so I have just said absolute pressure is the, so from here only you can understand that absolute pressure is the atmospheric pressure plus gauge pressure, right? So this is the option A, atmospheric pressure plus gauge pressure. Next, hydraulic press employs the direct application of Bernoulli's principle, Navier-Stokes equations, Pascal's law, Archimedes' law. So what Pascal's law states? So Pascal's law states that the pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and to the walls of the containing vessel. Right? So this is the Pascal's law, that if you give a pressure in an enclosed fluid, this fluid is transmitted to every portion of the containing vessel. So you have seen the experiment of balloon, right? A balloon full of water, and if we uh, make hole at all of the side of the balloon, then what will happen? The water will come out from all the holes, and it will be exactly perpendicular to the surface. So that defines the Pascal's law. If you want to see a video, I can show. So here you can see. I hope you can see, right? It is proving the Pascal's principle. What I have just said. Pressure applied in a confined liquid is transmitted uniformly in all direction throughout the liquid. See, piston and a balloon. So this is a rubber balloon. Fill the tube with water and pierce some holes in the balloon. See? So now they are pushing the piston downwards and water is coming out. So what is written? Push the piston downwards so that the pressure is exerted on the water in the tube. See how they are coming out. So you are giving force per unit area, and that is the pressure. You will observe that water comes out with same force in all the directions from all the holes, right? So this is the Pascal's law. Now what is the conclusion of this? So if the liquid is trapped in a container and pressure is applied according to the Pascal principle, this pressure will be transmitted equally in all directions and the water that moves out from the holes of the balloon with same force. Right? So you have understood this. So hydraulic press is also works on the direct application of Pascal's law. Oh, sorry, I have repeated the same question. Question number 4. The pressure in a homogeneous liquid at rest is the same at all points throughout the liquid, dependent on the direction, the same at all points at the same level, dependent on the density. So, in a homogeneous fluid at rest, that means the fluid is also not moving, the block is also not moving. If there is a block, that is also not moving. So, and it is a homogeneous liquid. That means this contains same molecule. Suppose there is water, and water is at rest. So, pressure has to be same at all the points, right? But it has to be at the same level, because we have just seen in the lecture that pressure varies with depth, but not it does not vary with the horizontal position. So pressure may be different at this position and this position, but pressure is not different at this position. This is the same pressure. So it is the same at all points at the same level. Next. A large open tank contains a homogeneous fluid at rest. Which of the following is not true regarding the pressure at the upper surface of the fluid? It is the same at all points at that level. It will increase if the density of the fluid increases. It will increase if the atmospheric pressure is increased. All the statements are true. So what do you think? Which sentence is not true? So in an open tank, so at the surface level, if the point is at the same level, it is same at the all point. It is true. Just now you have seen. So it will increase if the density of the fluid increase. So so hmm, so the answer will be, and the third option is, it will increase if the atmospheric pressure is increased. That is also true. The second option, it will increase if the density of the fluid increases. This sentence is not true. This sentence is not true. So this is our answer. Next question. A pitcher is full of water up to a height of 10 centimeters. The area of the bottom surface is 10 centimeters square, and that of the upper surface is 40 centimeters square, right? The atmospheric pressure is 101.5 kilopascal and the density of the water is 1000 kg per meter cube. Find the force exerted by the water at the bottom of the pitcher. What will be the answer? You think? So we have seen that the pressure varies with the depth, right? So P equals to P naught plus rho GH, right? So pressure varies with the depth. P equals to P naught plus rho GH. H is the height. H is the height. So now what we don't know. So it is said that find the force exerted by the water at the bottom. So find the force. So P0 we know. P0 is the surface atmospheric pressure. That is the 101.5. That means 10150 Pascal plus rho of water is 1000 kg per meter cube. Gravitational force is 9.8 meter per second square, and this h is 10 centimeter, that is 0.1 meter. So what is the pressure now? Calculate. So this is 102480 Pascal. It's a very simple problem. So now it has asked that what is the force. So now we know the Pascal, right? So pressure is force per unit area. Then force will be pressure into area. And as it has said that at the bottom surface, so we know the bottom surface area is 10 centimeter square. That means 0.001 meter square is equals to 102.48 Newton. So this is your answer. So 102.48 Newton, option B. Next, consider the following arrangement. Okay, so this is F1, this is F2. Force at 2 column. The force applied at the narrow arm panel is 10 Newton. The diameter of the narrow and wide panels are 1 meter and 4 meter respectively. Find the force 2. So in the lecture you have seen this type of problem. Let me go there. Where is that? Maybe I couldn't find it, so it is there. So what is the logic? So in the narrow panel, for the narrow panel, if you know the area and you know the force, then P will be F1 by A1, right? And the pressure will be same at both the point because it is at the same level. There is no distance, vertical distance between them, right? So now you know the P equals to F1 by A1. Now you know the pressure, and then in the white column you know the pressure and you know the area. Then F2 will be P dot A2, and this P means F1 into A2 by A1. So simply we will put these values. So it will come like that. F1 is your 10 Newton, A2 is pi d square by 4, right? So in this case pi d2 square by 4, and here pi d1 square by 4. So pi and 4 will be cancelled out. So what it is coming? 10 into d2 is 4 meter square, that means 16, and this is 1. So it is coming as 160 Newton. This is 160 Newton, right? Next question. Which of the following is based on a perfect vacuum? Which of the following is based on the perfect vacuum? So we have seen that, right? So perfect vacuum is based on the absolute pressure. This is written in the note. Perfect absolute pressure is based on the perfect vacuum. Next. What is the value of standard atmospheric pressure among the following options? So standard atmospheric pressure. So we have seen that 1 atm equals to 760 mmHg equals to 101,325 Pascal or 101.325 kilopascal or 14.7 psi. So it is the option A, right? Now question 10. Which of the following functions as a barometer? Which of the following functions as a barometer? So if I go back to the lecture, it was there, I think. See, it is written here. So open-end manometer, difference between the liquid levels in each arm. Okay, this is the open-end manometer. Second one is the differential manometer. So if I show you the corresponding image, it will be more clear. So open-end manometer. You can see this, right? So there is a valve and the end is open, that is called open end manometer, and there is a difference in the liquid in the arm. So this is the open end manometer. Differential manometer is used to measure pressure difference between 2 points. So differential manometer. You can see. So in the open end manometer, one end was open, but in this case, both ends are closed and there is a fluid difference, height difference. right? So this is a U-tube differential manometer, U-shaped. Okay, so this is the differential manometer. Next one is the sealed end manometer. Near vacuum enclosed at one end. If the open end of the sealed manometer is exposed to the atmosphere, the device functions as a barometer. Sealed end manometer, right? C. Sealed end manometer. So first one was the open end. So this here, this is the it is closed, and at one end this is the vacuum. It is said, right? There is a vacuum, and if that side is open to atmospheric pressure, that is called your barometer. So first we'll see the barometer. So you can see one side is vacuum and one side is exposed to mercury reservoir, that is, it is called mercury barometer. So now we'll learn what mercury versus manometer. So is there a video? We'll go for the video. So here you can see the difference between barometer and manometers. To measure the pressure of gases, and those are the barometers which is shown on the left side of your screen, and we have the right side is the manometer. You can see the difference, right? So this is a mercury barometer. So one side is vacuum, then there is a gas tube and it is open to the atmospheric pressure mercury. Starting with the mercury barometer. So this is a diagram over here of the basic laboratory barometer. And the barometer is used to measure atmospheric pressure. The pressure of the air that is all around us is called the atmospheric pressure. The mixture of gases, the oxygen and nitrogen and argon and CO2 and all those other gases that are present in the air are exerting a pressure. And this is how we can measure. So barometer measures atmospheric pressure invented by Evangelista Torricelli. Evacuated, basically just an evacuated glass tube, and the tip of the tube is submerged in a pool of mercury. So the word evacuated means the vacuum within this tube. So all of the air has been just sucked out of the tube, and then the open end of the tube is just dipped in a pool of mercury. So basically how it works. Atmospheric pressure, you have pressure of all of this pushing down and pool of mercury, and the downward pressure of the atmosphere is going to force the mercury up this column. And if it's you have normal average weather conditions and you are at sea level, it's always going to push the mercury up the column to an exact height of 760 millimeter Hg. So this is the pressure, that is how atmospheric pressure is calculated in a laboratory. Okay, that means this is a initially it is vacuum, and at one side it is open to the mixture of mercury or to the mercury solution, and now you can see that the mercury will exactly reach the 760 millimeter distance. So it is equivalent to the atmospheric pressure. It is equal to 29.92 inch, but again atmospheric pressure isn't always constant. Different conditions of our weather might influence the atmospheric pressure, so this can fluctuate even throughout the day. So it's always important that if you want to take the pressure of the atmosphere, you do it, just assume that it's going to be 760 millimeter of mercury. You actually use a laboratory barometer and measure the atmospheric pressure for that time. To measure the pressure of a gas that is not the air, well, then we would rely on the device known as the manometer. So again, the manometer measures the pressure of a gas other than air. Essentially, the manometer is a U-shaped tube. Within this U-shaped tube, there is a dense liquid. Here, usually will be mercury, but any dense liquid will do. It's a U-shaped tube, and one end of the U-shaped tube is open to the atmosphere. So we have the atmospheric pressure pushing in this direction. That means in the downward direction, the atmospheric pressure is pushing the mercury, already dense liquid, in the downward direction. And here it is connected to some kind of pressure gas. So basically the way it works is atmospheric pressure is going to push down this way. The high pressure gas is G, to going push down this way. So we have like a constant pressure. So to speak, we can measure what the pressure of the gas is relative to the atmospheric pressure just by recording the height between this level of mercury here and this level of mercury over the right column. Oftentimes, U-shaped tube is going to be mounted to a piece of wood that has a millimeter ruler attached to it. That way, measuring the height is fairly simple now. So you can see the diagram now. Left side is higher than this mercury level over here on this side. Well, that tells you that pressure of the gas is actually greater than the atmospheric pressure, because it's forcing this mercury up a little bit higher. If the opposite was true, then the atmospheric pressure is higher than the pressure of the gas, right? So this is how it works. So I think it is clear. So if you simplify this, then what does it say? That in case of barometer, the test tube is vacuumed first, then it is pushed into a jar of mercury, and if this is mercury here, and this mercury is reached to the 760 millimeter distance, then it is the 1 atmospheric pressure. It is the atmospheric pressure indication. And in case of manometer, if it is used to measure the pressure difference of a gas to compare to the atmospheric pressure. So a gas is filled here, and this is a U-shaped column, and this is open to atmosphere. Then there is a liquid, mostly mercury. This is also Hg. If this height difference is there, that means the atmospheric pressure, this is the high pressure gas is there compared to the atmospheric pressure. And if the difference is in low, that means in the tube, this is there and this mercury is in this position, then the difference is called, there is low pressure gas is there. Okay, so which of the following functions as a barometer? This is the sealed end manometer is called as the barometer. Next. According to Archimedes' principle, the buoyant force experienced by a fully or partially submerged body in a fluid is equal to the that of the fluid displaced by the body. What is the answer? So, if there is a block is submerged in a pool of fluid, then the buoyancy force experienced by this block will be equal to the weight of the fluid displaced by the body. Okay, so it is the weight of the fluid. Weight means mass into acceleration. Next. Okay, it is mass into acceleration. Next. If the metacenter aim of a floating body that is inclined at a small angle is located higher than the centroid G, which of the following will happen? For that case, we have to go to the lecture. So here comes the metacenter, stability of a fluid. So you can see what it is written. I am just reading, then I will explain with the diagram. So a body of weight W is floating in the water with an inclination of small angle theta, suppose. The location of the centroid G, you can see the centroid, right, does not change with the inclination of the body, which is true, right? If a block is there and its centroid is in the middle, if I rotate it a little bit, the centroid will not change. But since the center of buoyancy, this is C, but the center of buoyancy changes, moves to the new point C prime. A couple of forces WS is produced and this couple restores the body's position to the stability. You can see this W, right? It will try to restore it. The force of the couple WS are called restoring forces. The point M on the vertical line passing through the center of buoyancy C dash and the center line of the body is called metacenter. This is M is the metacenter. So G is the centroid, M is the metacenter, C is the center of buoyancy when the block was steady, and C dash is the new center of buoyancy when the block was little bit tilted. And this GM line is called the metacentric height. And if M is located higher than G, if M is located higher than G like this in the image, the restoring force acts to stabilize the body. That means the restoring force try to bring back the tilted condition to the original condition. But if M is located lower than G, okay, then the couple of forces acts to increase the roll of the ship, so make the ship unstable. So if M is below the G, then it will completely roll down. Okay, so depending on that, if the M is floating body inclined at a small angle located higher than the G, so the restoring forces will tend to stabilize. Right? This is the option A. Next. A tank is filled with oil up to a height of 2 meters. The specific gravity of the oil is 0.95. Find out the force at the bottom of the tank when it is being moved upward at an acceleration of g by 3 meter per second square. The area of the cross section at the bottom of the tank is 2 meters square. The g value can be taken as 9.8 meter per second square. So what do you think? So height is given, specific gravity is given, area of the bottom is given, and the acceleration is given, moving upward. So you can tell me what is happening. So here, so now the acceleration will change, right? So acceleration, because it is going up, oil is going upward, so acceleration will change. So the new acceleration will be, or effective acceleration will be, g is already there and this will be g by 3. So it will be 4g by 3. Okay. And now the pressure at the bottom is simply P equals to rho into G prime into H. So rho is specific gravity of the oil is 0.95. So it will be 0.95 into 1000, right? Because it will be multiplied by the density of water. Your G, new G is 4 by 3 into 9.8 and H is 2 meters, which comes around 24,826.66 Pascal, right? Now it has asked about the force. So again, F is equals to PA, P equals to this 24,826.66 and here A is 2 meters square. Then it is coming as 49.49653.3 Newton, which is equivalent to your 49.65 kilonewton. So it is 49.65 kilonewton. Next, two identical cylindrical blocks of wood float in water as shown in the figure. Choose the correct option. Higher pressure acts on the surface of block A and therefore it displaces a greater volume of the water. higher pressure acts at the surface of block A and therefore it displaces lesser volume of the water. The two blocks displace equal volumes of water. High pressure acts at the surface of block B and therefore it displaces a greater volume of water. So, even the surface area where the pressure acts in case of A is lesser than in case of B, but it displaces equal volume of water because from the buoyancy point in the Archimedes principle we have seen this. The buoyancy force is dependent. So, buoyancy force is dependent on the equal dependent on the not equal, it is dependent on the volume of the or weight of the displaced water or displaced liquid, right? So here in this case you can see that the surface, the volume of both A and B will be same, right? And the fluid is same. Here in this case it is water, right? So this weight will be same for all. So it will be rho Vg. This buoyancy force will be rho into V into G, right? So rho V will be the weight, right? So it is rho is same for same because they both are in same liquid and V is same for both of them. It is the same height, same identical cylindrical block, right? So this is the option 3 is correct. Next. A cylindrical vessel filled with liquid is rotating at a constant angular velocity omega. What will be the shape of the free surface of the fluid? A cylindrical vessel is filled with liquid. A cylindrical vessel, right, filled with liquid is rotating at a constant angular speed omega. What will be the shape of the free surface? So free surface will be, if we imagine it like this, so if you imagine it is like a pipe flow, so fluid is filled and free surface is this fluid. So this is the fluid is going. This is the fluid, suppose the front part of the fluid. This is the free part and it is rotating at a angular velocity omega, then this will be like this. This will be a parabolic flow. Right? Next, question 16. An open cubical tank of dimensions as shown in the figure was initially fully filled with water. When the tank was accelerated on a horizontal plane along one of its sides with an acceleration a, it was found to have spilled 1/6 of the initial volume of water. The situation can be explained as shown in the figure. Find the acceleration a, where a acceleration with which the container moves along the horizontal plane, I the height of the or L the height and width of the container, x the height corresponding to the spilled volume of the fluid due to the acceleration, theta is the angle of inclination, g is the acceleration due to gravity. So what will be the answer? So we will calculate the tan theta to calculate the A and G. To calculate the A. So this is the theta angle, right? So what will be tan theta? Tan theta will be A by G calculate tan theta equals to, that is, top distance is x, bottom distance is L. Also x equals to 1/3 of L. So this is 1/3 of L by L. This is 1/3. So again, if this is A by G equals to 1/3, then A equals to G by 3. This is the option 1, A. 17. What is the centrifugal head on the free surface in case of the rotational flow as shown in the figure? So the free surface, this is coming from dz dr, that is from the balance of centrifugal and gravitational force. This is dz dr equals to omega square r by g. Now if we integrate dz from 0 to z, and omega square by g can be taken out, then r into dr, sorry, from 0 to r, it will be giving you z equals to omega square r square by 2g. This is option D. Which of the following statements is not true for static fluids? No relative motion between the particles. Viscosity can cause shear stress to arise. Pressure varies with height. All the statements are true. Not true. So as a fluid is static, so no relative motion between the particles is really a true sentence. Viscosity causes shear stress to arise. That is not the that viscosity. If viscosity causes shear stress, that means it will help to move also. So that is not true for static fluid. Pressure varies with height. This is also true. So option is option B. Correct option is B. What is the center of buoyancy? What is the center of buoyancy? The center of gravity of the solid body, the center of gravity of the displaced liquid, the point of action on the weight of the body, none of the above. It is the center of the gravity of the displaced liquid. Okay. Next, when can the fluid inside a moving vessel be treated as a static? When there is a rotation in the liquid, which is not true. When there is no relative motion between the liquid and the container, this is true. When shear stress components are present, this is also not true. The fluid inside a moving vessel cannot be treated as a static fluid. Yes, because fluid, it is true actually, but this is not true, the static fluid. We'll do more questions. So, which of the following is only type of stress involved in a fluid at rest? So it is the normal stress. Which of the following is the only type of stress involved with the fluid at rest? So it is always the normal stress, right? This is the normal stress. Next, according to Pascal's law, how is pressure transmitted in a closed vessel? It decreases linearly with the distance. It is transmitted only in the direction of applied force. It is transmitted to all parts at the same pressure value. It acts only on the bottom surface of the container. It is option C. So Pascal's laws I have shown you at the start of this session. So it is transmitted to all parts at the same pressure value. For a floating body to remain in stable equilibrium, where must the metacenter be located? Think and tell me. Think and tell me. So we have seen in the case of this floating fluid, right? So this is the center of gravity is G. This is the center of buoyancy. This was the metacenter M. For a floating body to remain stable in equilibrium, M metacenter will be higher than at the center of gravity, right? So it is option C. Next, when a container is moving with a constant horizontal acceleration, what happens to the free surface? So the surface tilts to the horizontal inertia and the angle where it tilts at an angle AX by G. So this is the 10th hit. Next, a hydraulic press has a small piston area A1 and a large piston area A2. If A2 equals to 2 of A1, what is the output force F2 for an input force F1? So this is the case we have just seen it, right? This is the shorter area and this is the longer area. So in case it is F2 equals to P into A2 and P was F1 by A1 into A2. So here A2 is 2A1. So it is F1 2A1 by A1. So it is F2 equals to 2 into F1. Force is proportional to the area ratio. Next, A rocket carrying a liquid tank accelerates vertically upward at Az equals to g. What is the pressure at depth h? So now the effective gravity will become g plus g equals to 2g, and then pressure will be 2 into rho g h. That is option C. Next, a tank is accelerated horizontally at 3.27 meter per second square. If g is 9.81 meter per second square, what is the slope of the free surface? So tan theta is A by G, right? From the definition. So 3.27 by 9.81, it is 1 by 3. Calculating the pressure at a depth of 10 meter in a water pond. Assume rho equals to 1000 kg per meter cube and g 9.81 meter per second square, neglecting atmospheric pressure. So it is only the hydrostatic pressure at the surface, right? At the bottom surface. Hydrostatic pressure is the rho gh. It is the simple 1000 into 9.81, g is 10. So it will be 98100 Pascal. Option B. In a U-tube manometer, right? In a U-tube manometer, if the height difference of the pressure measuring liquid is h, right? If this height difference is h, the pressure difference delta P is obviously delta P equals to rho g h. Option B. Next. A rectangular sluice gate is 3 meter high and 2 meter wide. So what is telling? 3 meter height and 2 meter wide. If the center of gravity G of the gate is at a depth of 5 meter below the water surface, what is the total force Ft acting on the gate? So pressure will be the total pressure will be rho g, and this will be the 5 meter depth, right? So rho is simply 1000 into 9.81 into depth is 5. So it will be 49050 Pascal. And the force Ft will be P into A 49050 into A is 3 into 2, that will be 294300 Newton. Simply pressure height problem is option C. Next, a container of oil with a specific gravity of 0.85 is moved vertically downward with an acceleration of is a g by 2. What is the pressure at the depth of 1.5 meter? So the oil is moving vertically downward. So the effective G will be G minus G by 2. So this is G by 2, right? So now the pressure will be rho is 0.85 into 1000. G will be G by 2 and this depth is 1.5. So what is coming? So it is coming as 6253.875 Newton per meter square. Okay, the answer is missing, I guess, but this is the right answer. Maybe there is a printing mistake there. Next, an open rectangular tank is 4 meter long and contains water at a depth of 1 meter. If the tank is accelerated horizontally at 3.27 meter per second square, what is the rise in water level at the rear end of the tank? So, tan theta equals to A by G, right? So A is 3.27 by 9.81 equals to 1.3. So the rise will be tan theta into L by 2, length by 2. So this is Tan theta is 1/3 into 4/2 means 2. So the option is 0.667 meter. Next. A cylindrical vessel is rotated at a constant angular velocity omega if the liquid rises by z minus h naught equals to 0.04 meter at a radius of r 0.16 meter. Find the approximate value of omega square. So the liquid rise z minus h naught equals to omega square r square by 2g. So you have to calculate the omega square. So omega square will be z minus h0 is 0.04 into 2 into 9.81 divided by 0.16 whole square. It is coming as 0.04 into 2 into 9.81 divided by 0.16 whole square. It is coming as 30.656 omega square, that is close to this 30.6 radian square per second square. Next, a rectangular pontoon has a volume of displaced water V equals to 29.4 meter cube and a horizontal cross-sectional area of 21 meter square. What is the distance of the center of buoyancy above the base? So center of buoyancy is V by A, height of the object. Height of the object is 29.4 by 21 equals to this is 1.4 meter. So it will be h, the pontoon, in case of pontoon, the center of buoyancy will be h by 2. So it is 1.4 by 2, 0.7 meter. Next. Read the question. A 120 centimeter long tank contains water and air maintained at 60 kilopascal above the water. If the tank is accelerated horizontally at 10 meter per second square and the resulting surface tilt results in a distance x equals to 68.63 centimeter and y of 69.94 centimeter, what is the calculated pressure PA at the bottom leading corner? So, for the accelerated for the accelerated height portion. So it will be summation of all of three, right? So pressure at point A will be pressure at the surface, that is 60 kilopascal. You can see P gas. Next, the displaced portion pressure and the original pressure. So you can calculate 60 kPa. This is 60,000 pascal. Rho is 1000. X is 10 into L minus X is 68 point. This is 120. So horizontal pressure means 1.2 minus 0.6863, and this again comes to rho is 1000 into 9.81, and vertical pressure is 1. It is coming as is coming as 74947 Pascal. This is close to 74,900 Pascal. Next, a rectangular tank 4 meter long and 1.5 meter deep is filled with water toward depth of 1 meter if it is accelerated horizontally such that the rise in water level at the rear end is 1.1667 meter. What is the volume of the water remained in the tank? Assume width is 2 meter. The rise is 1.1667, right? 1.1667 minus 1, and the front it is 1.5 deep by 2 into width, length and width. It is coming as 6.667 meter cube. So it is option B. Next, an open container is moved vertically upward with a uniform linear acceleration Az. If the pressure is found to be this, what is the pressure at depth h if the acceleration is exactly half of the gravity, g by 2? So the new pressure will be rho gh into 1 by g by 2g. So g will be 1 plus 1.5, which is 1.5 rho gh. It is option C. Next, a vertical square gate 60 by 60 centimeter square has its top edge submerged 12 meter below the water surface. Using the density of water as 1000 kg and G is this, what is the total force acting on the gate? Total F will be rho G Hg into A. So this is 1000 into 9.8 into 8g is to already it is 12 meters submerged, and then this has a 30 centimeter distance, that is 0.3. So 12 plus 0.3 meter into A is 0.6 meter into 0.6 meter. So it is coming out to be 43438.68, which is close to 43458 Newton. Next, a cylindrical vessel filled with liquid is rotating at a constant angular velocity. If the pressure difference between two radial points R1 and R2 is governed by P2 by P1, what is the pressure difference if the fluid is water? So delta P The equation is already given, you have to calculate only. So just put the values. This is 1000 into 5.54 square into 0.16 square divided by 2. So what is it coming? So it is coming out to be 392.8 Pascal. Okay, next question. A differential manometer is used to measure the pressure difference between 2 points A and B in a water pipe. If the manometer uses mercury and the difference in mercury levels is 15.24 centimeter, what is the pressure due to this mercury column alone? So it is P equals to delta P equals to rho of mercury GH. The mercury is 13,600, G is 9.81 and it is 15, not 15, 1.5, sorry, 0.1524 meter. What is it coming? It is coming as 20.336 Pascal or Newton per meter square for the column alone, mercury column alone. A 2-meter wide rectangular gate is built into a bank at an angle theta. To the water surface. If the total force, if a 2-meter wide rectangular gate is built into a bank at an angle theta to the water surface. If the total force Ft is calculated as the product of the pressure at the centroid G and the underwater area A, find Ft when the depth to the centroid HG is 8 meter and the underwater area is 0.8 meter square. So there is a water and this is angle at a theta. Right, and this G is 8 meter underwater. This is 8 meter underwater. So what will be the FT? It's simple, rho G H G into A. The area is 0.8. So it is coming out to be 62.784 Newton. I'll open a rectangular tank 2.5 meter long and is accelerated at a 2 meter per second square up at a 30-degree incline. What is the calculated slope tan theta of the free surface of the liquid? So tan theta is vertical by horizontal. So vertical one is the 1.732 and horizontal is 1 plus 9.81. So this is coming out to be 0.1602. 'A cylindrical vessel is rotated at a constant angular velocity at the axis of rotation. The liquid depth is h naught. Using the relationship, calculate the z. Radius r if h0 is 0.2. Okay, so this is pretty straightforward. So z will be h0 plus r square omega square by 2g. 0.2 plus 0.16 square, 5.54 square, 2 into 9.81. It is coming out to be 0.24 meter. Option B. A floating body has its center of buoyancy located 0.7 meter above the base and our metacentric height cm is 0.536 meter. What is the maximum height of the center of gravity above the base OG for the body to remain stable? So for the body to remain stable, we know that M has to be in the higher position than G. So OG equals to OC plus OM equals to OC's distance is given as 0.7 and OM, not OM, this is a CM, sorry, OC plus CM. it has to be 0.536. So it is coming out to be 1.236. So this will be this. So the maximum height of the center of gravity will be 1.236 meter. A thin wall cylinder with a diameter of 0.5 meter is used as a pressure tank. If the internal fluid pressure is 200 kPa, what is that force acting per unit length of the wall to resist tearing the cylinder longitudinally? It is balanced by internal pressure. So it is balanced by internal pressure. 2T equals to P into D. T equals to P into D by 2. P is 200 kilopascal into D is 0.5 by 2. This is 50 kilonewton per meter. Next. The hydraulic force F1 is applied to a small piston with a cross-sectional area of A1. If the output force F2 required is 5000, what must be the ratio of the larger piston? So we have already known that F2 is equals to F1 into A2 by A1. So A2 by A1 will be F2 by F1, that is 5000 by 500, that is 10. A 60 centimeter square gate is hinged at its bottom edge and inclined at an angle of 45 degree. The total force acting on the gate is this, and it acts at a center of pressure, while the centroid is this. What is the momentum force per unit length needed to just open the gate? So momentum force is the total force into its diameter by its length. So it is 43130.0.3 by 0.6. It is coming as 21940 Newton. Rotational is 9.81. So it is the same equation we'll be using, H equals to omega square r square by 2g. So it is coming as h equals to omega square r square by 2g. So omega square equals to 0.04 into 2 into 9.81 by 0.16 square equals to 0.04 into 2 into 9.81 divided by 0.16 square, and root under it is coming as 30.656, and omega is coming as 5.54 radian per second. It is option B. So this is for today. So I hope you have understood. I have solved a lot of problems to sail through your this week assignment. I hope you will find this helpful. Next week will be not meeting at the same time or same day. Today, next week's class is little bit shifted. It is supposed to happen on 6th February, but it will be happening on 9th February, that is Monday. But the timing will be same from 7 to 9 p.m. Okay. Hope to see you there. Till then, thank you. Goodbye.